Hello community! Let's continue about AI reasoning optimization. In my last video we stopped here and I showed you here our new framework to help our proprietary LLMs like GPT-4 Omni and Gemini to reason. Now, I told you we have three frameworks and you know those frameworks. The first is chain of thought. I have here a video where I show you here the connects to instruction fine-tuning, or if you want chain of thought with a React model. Second is tree of thoughts. You know these beautiful ideas where we do not have here just multiple chain of thoughts together, but we have now branches that branch out here, and you have here the classical tree of thought structure that later became also enabled by a backtracking from a specific branch, from a specific chain, so you could go back and explore different manifolds. And then, you know, the third classical one is the graph of thought. And here in this video about 8 months ago, I showed you that the graph of thought performance for AI reasoning is better than any chain of thought variant that you can imagine. This graph of thought is really interesting. And you remember the basic idea was thoughts are vertices on our graph and the dependencies between our thoughts are the edges. And this enables us some novel transformation of the thoughts. Since this system is also non-linear, we're a little bit closer here to the human neural structure, and graph of thought reflects here this with its beautiful graph structure. You remember the publication? Please note this is version 4, an improved version of the original paper, Graph of Thoughts, by ETH Zurich. And they showed you here beautifully when to use what methodology. So you have here at the beginning single chain of thought, multiple chain of thought, then you have tree of thoughts, and then you have arbitrary graph. And what I did not notice, there is even two different models for a tree of thought with dashes and a tree of thought model without the dashes. Nice. So the new part is now for the graph of thought that we are not anymore linearly restricted like here in chain of thought or multiple chain of thought, or that we are operating here in a two-dimensional manifold like a tree of thought. But now here the graph of thought is n-dimensional to build. Think about our feature space when we have here our embeddings of our inputs. So graph of thought opens up here our complete tool set of graph analyzation. Of course, please always be aware when you ask yourself, hey, who or what decides when to follow here a specific link or when to backtrack here from a chain or split in different chain. What is the causal reasoning capabilities that are here in play? This is, of course, our LLM, specifically the pre-trained dataset, the quality of the pre-trained dataset of our LLM or our vision language model. For my green grasshoppers, here a short system overview of the architecture of a graph of thought. You see we have a user, we have our LLM. Remember we have here the controller that controls here the complete operational thing. Then we have our prompter, our parser, and the scoring and the validation with the ranking happening here. The structure of the graph of operation can be in different forms, and we had a look here at the code. If you want to see a really completely throughout defined example, here this is for you. Of course, here we have also by GitHub here the code available for you. Now, as I told you in my last video, we have now, since 4 or 5 days, a new reasoning structure that should be better than at least a chain of thought. So let's have a look at this, and it is called an abstraction of thoughts. From June 18, 2024, you have here the researcher from Tsinghua University in China, and they show us here in their research paper that reasoning with abstraction is better. Now, the idea is simple. Instead of going through here a concrete example, you have kind of an abstraction layer where you say, what is exactly my task, my query given? can I find here and let's say abstraction where I have a solution template already to solve this, like here for a quadratic equation. So then I just have to substitute the coefficient in my general solution, and then whatever are the values, I just follow here and I come to the correct conclusion. Now, of course, this is the most simple case. Another one is here, I have 1 orange, 5 raspberry, 2 books, 3 plums, a pencil and a grape. How many fruits do I have? And now the researcher developed here a huge data set for abstraction of thoughts. And for example, in this example, they said, hey, first step, identify the fruits from all the items, because the task is how many fruits do I have? Then you identify the number of each fruit, and then you sum up the number of those fruits. Beautiful. If you think this as a toy world problem, this is easy. So imagine you have your little constructed toy world where you can solve everything that you will encounter with, let's say, 100 solution templates. So each and every problem that encounters in your real toy world, you can reduce to one of those 100 complex abstract solutions or problems. So you see what you have kind of an abstraction cascade going on. But the nice point is also you can do this with code. Here on the left side, you see the chain of thought augmentation. And here on the right side, you see here the abstraction of thought here for this task. And as you can see, all the abstraction, for example here, perform here a breadth first search on the two-dimensional maze to find the shortest path length from start to end. This is now here, if you want, an own function that we define here in this abstraction. And it's like we use some modules, some Lego parts, and then we put it together and fill it with specific values. Let's come here to the result that the researcher found. Just want to show you here the performance indicators. So they say that their experimental results indicate that the models aligned here to the abstraction of thought reasoning format substantially outperforms those aligned to a chain of thought in many reasoning tasks. Now, let's have a closer look, because it's not really that simple, and there's a lot of beautiful things hidden in this analysis. So at first, if we want to do this, we need here a benchmark. Now we go here to Google Research and Stanford University, and the end of 2022, they published here this big benchmark BBH, and here you have the complete publication. You can see here each and every task, but this is an established benchmark. And then they said, let's fine-tune some open source LLM on specific dataset. And they went here with the chain of thought collection, and here you have the publication, where they have, 1.84 million rationals across 1060 tasks. So beautiful, we have here a standard chain of thought collection we can use as a dataset to be fine-tuned on. And of course, the other nice thing here from Tsinghua University, they created also a abstraction of thought dataset. They call it collection, where they have here all their tasks that they train the system on. But please careful, this collection here is a purely synthetic AI generated collection. Now, it has an amazing amount of training data, 348,000 high quality reasoning processes are there. But remember, they're all completely synthetically generated. You remember in my video where I showed you about the law texts that are generated by an AI, that in some systems we have 30% of the answers given are hallucinated or contain hallucinated facts. Imagine here in this set that is also AI generated, and let's say we only have 100,000 data. But if we even reduce here the failure rate to 20%, of those 100,000 training data sets, 20,000 data sets are simply plainly wrong, incorrect. So whenever you use such an amount here of syntactically generated data that you can't manually as a human control 348,000 data sets here for causal correctness, you have to be aware that in this data set there is a certain amount of examples that may be, how to formulate this, not optimal. Beautiful. So here we have it. We have a benchmark and we have a chain of thought data set. We have an AOT collection, and what open source model we're gonna fine tune? Let's go with a Llama 3, 8 billion. Let's go with a code Llama. Let's take just a reference to the old data, a Llama 2 7B and a Mistral 7B. Then benchmark is of course ChatGPT and GPT-4. Now this is really interesting, but let's have a look at the models that we have. At first we have the pure Llama 3 8B pre-trained only model. And as you can see, we have here a task that is for a chain of thought and a task or a prompt that is for an abstraction of thought. Then we have the official Llama 3 8B instruction fine-tuned models. And now we have those new models by our colleagues from Tsinghua University, and they trained here a Llama 3 8B on the COT collection and on the AOT collection. So you see we have here a beautiful summary of the performance, and they did here this schema for Code Llama, for Llama 2, for Mistral 7B, and of course they could not pay for fine-tuning GPT 3.5 Turbo or GPT-4 Turbo, so here we only have the original versions. Now let's have a look. We have here now the result for a set of tasks for NLP and a set of tasks for algorithms, and then the sum of both. Have a look at this. This is kind of interesting. Let me start with Llama 3. At first, if we go, let's look only of chain of thought. If we go only with the pre-trained model, we have for NLP 63.6. If we look at the instruction model, we get 66. And if we then look here at the COT fine-tuned, we only have 51. So this is interesting because this shows us here that 63, 66, and 51, this is not really, this fine-tuning that happened here with this chain of thought significantly reduced the performance even compared here to only the pre-trained Llama 3 8B. And if you can see here, the jump here from a COT to an AOT is here about 5 percentage points, but here it is much smaller since we already have an instruction fine-tuned model. Now let's have a look at Mistral. Here we see, and we stay here with NLP, 61, 54, 61. So I would now argue from this data, if it only concerns here the chain of thought performance, that the performance of the instruction fine-tuned model is worse than the pure Mistral 7B only pre-trained model. And even if I fine-tune my Mistral 7B on a specific COT collection, I only achieve about the same that I achieve on the only pre-trained Mistral 7B for a COT task in the normal NLP tasks. Beautiful. Now the situation changes if we now look at the AOT task here. We go from 68, 69, 73. And 73 is also the best performance system here with Llama 3. So here, the fine-tuned Llama 3 8B pre-trained plus the AOT collection fine-tuned is now really showing its performance. And if we look here a little bit further in the algorithmic side, you see with 92%, this is a real excellent result. So in, let's call it pure speech or here an algorithmic, it really shines if we have here more algorithmic or code-specific structures. Now, same more or less here with the Mistral 7B. If we look at the AOT, and AOT, 62, 56, you see the instruction is not so powerful if you have here COT or AOT prompt structures. Keep this in mind, go with only the pre-trained model. But if you fine-tune here those models for specific call actions, well, yeah, 61 is also comparable here to the, let's call it naked Mistral 7B, to the only pre-trained Mistral 7B. And 71, yeah, it is 10 percentage point, but okay. However, again, with the algorithmic structure, this changes here to 84, which is really, really nice. Now, let's look at GPT-4, and here we can't afford to fine-tune this, so we have here just the prompt structure, either is a COT or an AOT, and you see they are about equal. So there's not much difference for a GPT-4 model. However, if you look here at the algorithmic, and these are all, by the way, 3-shot evaluation performance data on BBH that I just showed you, there you see that if you use here the abstraction-of-thought methodology, you can reach 97% evaluation performance on a 3-shot prompt testing out here the BBH. Quite interesting to see, really some interesting data, some beautiful comparisons showing us the pre-trained, the fine-tuned, the specific fine-tuned model, and how sensitive the model is to a specific chain of thought or abstraction of thought argumentation. And as you can see, the jump for GPT-4, for example, if we look here from 87 to 86.7, is about equal, but the jump here in code or other algorithm is really significant. They also had some beautiful analysis of the errors. So whenever the system produces an error, and they are relying here, of course, on the Llama 3 8B abstraction-of-thought fine-tuned Llama 3 model. So whenever an error happened, what is the cause of this error? And they found out that the reasoning error, the logical reasoning error, is about 38%. However, they have here hallucination as a separate entity. So reasoning error is incorrect conclusion from given conditions, and hallucination is misinterpretation of given conditions. If you look at the data, for me it is really not that hard to distinguish between a misinterpretation of a condition and an incorrect conclusion of a given condition. So let's, for the sake of simplicity, put these two together. So we have 38 plus 9, so we have 47%. Let's say 50% of the error types that occur in our abstract fine-tuned model, we have reasoning and hallucination. And then the rest is interesting. So you see a new way, a new really interesting way to have this, especially if you go here for the open source model, where you have here, for example, a normal chain of thought with 63. Now you can achieve here about a 73 performance jump. Or if you go with a Mistral 7B, also from a 61, you go to a 71 evaluation performance of a 3-shot. If you want the data of a 0-shot, they are also published in this publication. So you might say, okay, this was number 4, but you said, hey, maybe we have some idea about a next model. Now, it is rather simple what we do. We know that graph of thought is really powerful, and this new abstraction of thought is also kind of interesting in a specific use case, I would say. So what happens if we combine those two models? Now, it is not as easy as you might think. But let's face the question, can we combine both models and how to do this? Now again, abstraction of thought focuses on structuring the reasoning process into different levels of abstraction, starting from a high-level overview and progressively integrating more detailed information. Graph of thought is now non-linear, a more flexible relationship between our sorts. And what's so nice, this graph structure supports some dynamic updates and modification that we can adapt more fluidly to the task. But of course, you need compute infrastructure, because if you have a real complex graph structure, this needs some powerful infrastructure. Okay. As I told you, the graph of sorts is not limited to a two-dimensional manifold or whatever vector spaces, but here we can really think about the feature space that we had in our embedding of our vectors. We can go here to higher dimensional representations. And this makes it also interesting, especially here if you want to combine it with some abstraction of thought idea. For my green grasshoppers, to give you just a feeling what I'm talking about here. So let's say we have a graph of sort and we read an article about causes of increased respiratory illnesses if you live in the city. And our graph of sort machinery, if you want, our code generates, for example, this graph of the text. So you see, you have here your respiratory illnesses. And now out of the text, we have identification of contributor. So we have an air pollution in the city. Maybe we have the indoor air quality. We have some industrial emissions from the city or close by the city. We have maybe seasonal allergies that might dampen or more accelerate here whatever respiratory illnesses you can have. Maybe the traffic congestion right in front of your window plays here a role. And you see on the edges here, taking, for example, a scientific publication on this topic, identifies here, for example, here's a strong relation, this is a low relation, this is affected by. So you see, this is a very simple way how we can build here a graph of sorts if we have a given system. Now, if you do it a professional way, you know you can zoom in, for example, to this master node, and you will see that air pollution consists itself of a very complex graph of hundreds of sub-nodes and hundreds of sub-edges. So you can dive in, you can zoom in here into this graph if you have the compute infrastructure for this. But it is really easy to see immediately here main contributors, for example, respiratory illnesses. To understand how it works, let's have a look at the graph of sort, and let's take an easy example. We want to optimize here a traffic light system in a city that is polluted. So what we do, what happens now in this methodology? Now at first we have to create here the initial graph, the very first one. So we have a vertex creation phase, where each vertex represents a state of, for example, an intersection, or a traffic density, the time of a date, current light status, whatever. And then we have to create the edges, as I just showed you. And the edges represent transition between the states based on action like changing the light or updating traffic conditions or whatever there is. Then we have the phase of the data collection. So we gather real-time data from different sensors on the traffic flow, camera, sensors, whatever you have, and we input those here in the vertices of the graph, and the graph can have multiple factors. Use now this model to evaluate here each vertex for the traffic efficiency, such as the average wait time at the light or whatever, so you get here an idea about the state of the system. And then, as new data arrives, we have a continuous data stream bringing us real-time data. We can update the graph with new vertices, with new edge correlation, reflecting here the changes in the traffic in the light pattern. And then, and this is why we did all of this, we have our graph toolbox, and we open our beautiful shiny graph toolbox. For example, here we want to find the optimal path by a specific graph structure, so we implement an algorithm like A-star or Dijkstra to find here the path through a specific graph or a subgraph that results, for example, in the least overall wait time. And then we just have to implement this, whatever is the insight from this graph analytics. Now let's have exactly the same task now in the abstraction-of-thought model. As we know, we have here abstract layers. So we started with the high-level abstraction. We conceptualize here the problem in terms, let's say, of peak and off-peak traffic hours, and the objective of minimizing here the wait time and the congestion and therefore maybe the pollution. Then on a mid-level abstraction, we define specific traffic patterns in advance, such as the influx of vehicles on specific parts of the city or specific interconnects during different times of the day. We connect it to other events. Maybe there was a football game or maybe there was whatever. And we have, make it real simple, at low level. And here we focus on individual light phases and their duration adjustments. And then we formulate here a general theory that longer green lights during peak times could reduce here the congestion and reduce here also the pollutants. So we analyze the traffic data to verify if this condition is true. Then we have a refinement phase of the hypothesis, we have the implementation phase, and then we have an adjustment phase. But you see, this is highly theoretical. And you have, for your specific problem, have this, let's call it a solution template, where you have the correct abstraction formulation, the correct mid-level abstraction, and then it's broken down and coherently going down to the lowest level of your general theory. So it sounds easy in theory, but I think if you implement it here, you have a lot of complexity to take into account if you formulate your theory. So for my green grasshoppers, very short summary. So what we have. In this example, and we go here with abstraction-of-thought, it starts with a conceptual framework and refines this framework through specific data-backed steps, making it more structured and perhaps easier to validate and explain. So this model is strong for systems where changes can be planned in advance and implemented in stages, allowing here for a systematic analysis if you go here through the complexity levels of your hierarchical system. However, if something happens, you need a much more flexible, a highly adaptive and data-driven system where you have, for example, the focus on dynamically creating and adjusting a network of possible states based on real-time data using graph algorithms to find the best traffic light pattern. But you see, both systems have their strong points, and the intelligent way how we combine those systems, this is not a challenge. Now let's say we have an accident somewhere in the city, a major intersection. How do the system respond? What we have, if we want to build the systems, what we have to take care of, and how do we design the architecture of the system? Okay, so again, graph of sort, we look here, an accident happened. So the system now detects an accident through its sensor data or reports wherever they come from the traffic monitoring system, and immediately generates here a new vertex. We have a problem, we have a new sort, an accident is happening, and this has to be integrated here in the dynamic graph structures. Now, new vertices are connected through the edges to the existing graph or subgraph complexity to reflect possible state transition due to the accident that is happening within the graph, such as increased traffic congestion or redirected traffic flow, which routes are open here where people could escape here. And then the graph algorithm re-evaluates here the optimal path, considering the updated graph to minimize the traffic delay. You adjust the traffic lights accordingly. The situation comes now to an equilibrium. If the accident is finally cleared, the graph is updated again and reflects this new state here of a traffic flow, continuously optimizing the response. But what is nice, you know now, at a specific time of day, let's say in a correlation with a football game that happened just 3 blocks away, that we have now new vertices and new edges in our graph that are sometimes deactivated if you want, but whenever there is a football game in town, you know, oh, careful, there I have already my vertices and my edges integrated in the graph network to take care to respond immediately with proven actions. This is the power of this graph-of-thought methodology to help our LLMs reason if they don't have it in their parametric memory. Now we look now at exactly the same case here at the abstraction-of-thought level. We have an accident. This triggers here a new high-level abstraction in our LLM that has now to develop a new abstract plan. So this means the LLM has now to know exactly what is the situation in this part of the city, what is here the conditions that I have here in the 2 blocks surrounding here the accidents. How could I theoretically have a quick clearance of the accident site? Which resources do I have to activate? How can I minimize here the overall traffic disruption? Coordination here with emergency services, public information systems. And the LLM has in its pre-trained knowledge to come up now with detailed plans that are now formulated by the LLM under this new abstraction to reroute the traffic, extend here green light phases, for example, to lead to alternative routes, or even temporarily suspending here regular traffic light cycles to prioritize here emergency vehicles and so on. So you see, the complexity level of developing new plans is not really an easy task. And then those plans have to be refined, and if everything returns to the normal state, you have to reassess the entire situation, and you can prepare yourself for future responses. So you have now 2 systems, the same event happened, our accident, and you have now, let's say, a different multimodal view on the same event. And the interesting thing would be now to combine the system, the strength of a dynamic graph system, and the strength of a forward-looking, strategically oriented, what could happen plan that we can immediately implement through a graph structure. So those are my thoughts. But whatever we do, remember, whatever is decided by the system is decided by your LLM, by your LLama 3.8b, by your GPT-4 Turbo, by your Omni, by your Cloud 3.5, or maybe if you see this video, Cloud 4 system. It all depends on the LLM. And the LLM has to have the reasoning capability to cope with the degree of complexity that it will encounter in this accident situation. It has to have the reasoning depth trained on that it can find optimal solution. So based on real-time data from, let's say, the city is Chicago and from the last 10 years, so every accident that happened in the city of Chicago, when, at what time, why, what happened, was what the consequences, how it was resembled, and. And all of this has to go into the pre-trained data for this LLM. So this LLM is able to make the decision here for a traffic congestion management system for the city of Chicago. Great. So for my green grasshoppers, very short summary again. Let's make a break. So in the graph-of-thought approach, the LLM dynamically constructs and updates here the graph features by adding new nodes and new edges. Each node represents a possible state of the system, and edges represent a positional transition based on real-time decision and action taken as decided by the LLM. And the decision to add nodes and edges is based on the analysis by our LLM, highly adaptive, continuously evolving the graph structure as new data comes in, and based off the last 10 years of accidents in the city of Chicago. This abstraction part relies now on defining new high-level strategic plans to incorporate in advance when you have time, when you are relaxed. The LLM can take days and weeks to analyze all events that could theoretically happen given here its pre-trained data. And those new events and those new sub-strategies must fit within the existing reasoning framework, within the existing pre-training data set that this AOT will rely on. So this integration is not as easy as you might think. We have here some multiple levels of complexity you have to cope with, especially here on the pre-trained data set. This integration can be here in a clear way, in a structured way, follow here a clear method, so we can ensure that each new plan, each new subplan, each new adjustment contains here the optimal coherence with the overall traffic management system strategy. So, how we bring this now into one system, or maybe we should have two systems? What do you think? Now, of course, it depends on the pre-training data and the quality of the pre-training in general. Just as a reminder, pre-training is so important here for the knowledge to integrate in the LLM, to develop the reasoning abilities. They're mainly done during the pre-training, not so much during the fine-tuning. And about adaptation and flexibility, it is so important to have here the right pre-training data set. So this means now the artificial intelligence of an LLM, shaped by its pre-training and ongoing learning experiences by some continuous data stream, is critical in determining how effective it can implement a graph-of-thought and abstraction-of-thought strategy to handle dynamic and complex scenarios, maybe even in the planning phase. Now, you know me, in my last two videos I showed you about transfer learning. If you remember about this video where I showed you Apple multitask, multi-modal transfer learning optimization, think about this. Have a look at the video, come back, and then you understand what I say here. LLMs adapt a transfer learning where skills learned in one context, let's say in a graph structure, can be applied to another on an abstract level. And understanding the causal relationships in graph-based reasoning can improve the model's ability to form hypotheses and draw conclusions in deductive reasoning tasks. And this is why we do this. We want to have the benefit of both systems, of both methodologies. So at first, if we go for this, also for this transfer learning, we have to make sure that the incoming data are here standardized, that this data stream is coming in perfectly to our system. And the first question is, do we have separate, let's say, databases for the graph system and for the abstract logic? Or how do we deal here with incoming data streams? Yeah, worth mentioning the benefits of this transfer learning from both reasoning types. You have a more robust decision making in this hybrid system, and you have better predictive capabilities and a better performance of the overall system to proactively manage here the traffic flow in a city. And here we come now in a different topic. You know, we started here by causal relationship. We went over to a little bit of logic. We went to reasoning process. But now, and it happened pure accidentally, I can tell you, if we now combine here the abstraction plan that we get plus the dynamic graph in real time for an optimal path calculation in our multitude of high-dimensional manifolds, we are exactly at the planning. And planning will become important for the application of AI. So we are not anymore restricted to reasoning, but we have now complex system. We want to apply reasoning to complex system. We want to understand the future evolution of those systems, given there are disturbances, that there's a non-equilibrium phase of our system parameters. And therefore, we are now coming more and more into the planning phase of complex system and how we can implement AI system. And yes, I've chosen this particular because I am currently experimenting exactly with the combination of a graph-based AI system with an abstraction-of-thought system for the planning phase. So you see, reasoning, planning, and complex system application come together more and more. So how do we build a unified system of graph and abstract logic intelligence? Now, easy, no? A hybrid system here of a graph of thought and a abstraction of thought, you have here, I don't know, an interconnected layer, no? Where we have the data transfer between those systems. And you might say, yeah, of course, a shared contextual layer that we have done in the past on simpler system, and combines here or allows the model to cross-reference and combine the findings from both reasoning methods, enhancing its overall decision-making capabilities. But however, if you look closer at this, you get into some data, data normalization topics that are not easy to resolve. So what we do, hey, we are working here in AI research. So we ask ChatGPT for Omni, Super, Turbo, whatever. Hey, how we do this? And you know what? ChatGPT comes back here and says, yeah, no problem. Yeah, I integrate here the graph of thought and the abstraction-of-thought system. We build a minimal hybrid system architecture. We integrate the reasoning module. We have a data handling. We have an interaction interface. We have an efficiency. And that's it. No? And you say, yeah, but how do we build this? And you read it and you recognize this is just the old model architecture, now kind of transformed to this idea of a graph and an abstraction of thought. But this is just a pattern that was learned in the last years, and now GPT-4 just tries to apply this old pattern to the new terms, which, you're gonna be surprised, is not really working. But GPT-4 is not the only one. Let's take Claude 3.5 Sonnet. Makes it even simpler. You have an input processing module, you have a task analyzer, then we have two different engines. We have a graph of thought engine and an abstraction of thought engine. And then you have a hybrid reasoning controller. And I thought, well, this is a marketing term. I like this. No? And then you have an output generation module. What could go wrong? No? This is all that we are given. So, it is not that easy, and AI does not help at all if you want to be creative. AI just knows old historic patterns, but has real problems to come up with new architecture, with new solution for this. But why not follow the idea? And I wrote this. I said, okay, so somehow we have to develop here a knowledge base that feeds both systems, the graph of thought and the AOT. So in this includes here structured data, historic data, that can populate here the graph nodes and edges for a GOT and a hierarchical abstracted data representation that we need for the AOT reasoning. We have to ensure that the system is integrating here with the real-time data for both frameworks, and we have to somehow come up with a joint training strategy. Because it's not working if we have two engines and either we retrain engine A and then retrain engine B. No, we have to have a joint training strategy because we want to have here the utilization of the benefit of this hybrid system. We don't want to have two systems that we switch on and off. So another thing that I was fascinated with was this multitask learning approach. I want that the system is able to have a multitask learning functionality where the LLMs learn here to switch here between the best system depending what the scenario deserves and then integrate it back in the feedback loop. And of course, we need some reinforcement learning here for this particular task to fine-tune here the decision-making process of this hybrid system. So you see, we come closer to the system, and this is the way how you build in a hybrid system. But of course, by pure accidentally happening, or how should I call it, if we look here at one of my last video about Apple, this new multi-modal and multitask system that Apple developed here with here the specific tokenizers and the normalized tokenizers, I think this gives us here the solution how to proceed with our joint hybrid model. Do you remember what we had? We had an RGB image, for example, and with this 4M21 model, this vision language model, we were able to define the segmentation, the depth structure, the surface normals. We could identify human, we could identify all the metadata, we could form here the complete edge manifold, all the instances. And this happened here with this underlying power of this optimized multimodal tokenizers. You remember in the Apple video I showed you here exactly this piece of information, that we have a complete transform architecture with an encoder-decoder structure, and this makes it ideal to handle discrete tokens derived from multiple modalities. And I showed you that this system was able to handle RGB tokens and RGB pixel data. And in the video you saw that we had 4 multimodal tokenization modalities that we used, also as an encoder, as a vision transformer backbone. Now you remember the video where we're talking about our LGGM, our large generative graph models. They were based also on a vision transformer backbone, but now they are even simpler because they have a discrete tokenization. So what is the idea? Simple. Put here the discrete tokenization, and more or less this should give us here the architecture inspired by Apple to build our new hybrid model. But well, we better be fast because there is quite some competition in this area. AI research in this topic is really hot. Let's have a look at the competitor. Now, some days ago, I don't know if you noticed it, but Meta published here, almost on the same day that Apple published here its new multimodal multitask 4M21 AI, Meta published here this paper here also on multimodal models. And you might say, what a coincidence. Well, it is not really a coincidence because this model and the architecture and the technology that this model used was introduced more or less exactly a year ago, July 14, 2023. And you have here AImeta.com, the blog, introduce here the Chameleon or CM3 Leon, a more efficient state-of-the-art generative model for text and images. So real close what Apple came out, but their technology was based on CM3. And I digged into my archive and I found here at the in beginning of January 2022, there you have the original paper here from Facebook, that they kind of invented here CM3, a causal mask multimodal model. And this technology from beginning of 2022 was announced in 2023, and now in June 2024 is now announced as being operational and available to the public. Almost on the same day as Apple published its 4M21 model, also a multimodal model that has a real similar technology under the hood. And you know me, I wanted to have access to this model, so I went there and I clicked on this, and you know what I got from Meta? Here, a form you have to fill out to request access to the Meta Chameleon AI system. Now, isn't this beautiful? It kind of reminds me of something I've done years ago, I suppose, with Meta also. And of course, we have here a Chameleon research-only license with some quite heavy restrictions. So, yes, beautiful. So maybe we come to the common insight that this is not an open source model. And when you get access to this, you know that it is not a multimodal model because, as I told you here in my community tab, Meta restricted the output of this model to text only. So to call it multimodal in the output is a little bit of, how to call this, a marketing term. No? Beautiful. So yeah, I go with the Apple model. It is open source. So here we go. Yeah, it's a long video. Let's come to an end. The idea is here as a fifth mode of operation to support our proprietary LLMs that are not able to solve simple 4-line of text causal reasoning problems. I showed you 5 different modes. This is the 5th mode, the combination of graph-of-thought or abstraction-of-thought. So if you want to do some work at your university, if you want to publish a new model, my goodness, you have so many options right now. This is such a hot topic in AI research. Apple is fighting for it. Meta is fighting for it. So why not position yourself with some interesting publication in this topic? I think this will be multimodal and multitask. This will define our future. But currently, I honestly have to tell you, the research by Apple here is really here leading the way forward. And I will kind of focus here my research more and more here on this beautiful idea that Apple had here together, working together with the research team in Lausanne. Beautiful. Let's say we stop for today here in this video, and in the next videos, if you want, we can further develop this idea, or let's have a look how you respond in your comments to this video, what you are interested in, what you would like to see. But for a research, I think it is an absolute fascinating moment in time to really develop here new multimodal, multitask models that really are the next step in the evolution of AI systems. I hope to see you in my next video.